No. Okay.
Cek, cek. Yamamoto Sensei.
Hi. Hello.
Halo. Oh, Genki, desu ka?
はい。
Are you fine?
I'm fine. And, エコはどうですか？ And you?
Okage-sama desu. Genki desu.
ああ、素晴
I'm
ら
fine.
しいです。
Also fine.
素晴らしいです。
Okay, time we meet in the Zoom after
Yes.
uh, last year we meet in Tokushima. Remember? I also invite Kawai Sensei, but I'm not sure he can join or not.
Mhm. Oh, Kawai sensei will attend.
I'm not sure, but he asked to me if I can join or not. I said yes, you can. Also, of course you can join, but until uh, we do not Kawai Sensei attend here. Okay, no problem, Yamamoto Sensei.
Yeah.
Okay, wait a minute, maybe 3 or 4 minutes later.
Yeah, thank you very much for your, how to say, and background.
Yes, the same also. I also very thanks for your change to join this lecture. I hope your sharing is very useful to my student or me, of course. Hah? Suci, Mbak Suci?
Yes, Prof.
Ya, one.
Okay, we will start
Silakan.
our event. Okay, good afternoon, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Welcome to online today's general lecture organized by Department of Physics, Universitas Diponegoro. Allow me to introduce myself. I am Suci Faniandari and I will be your host for today's event. Before we begin, kindly allow me to share a few reminders. Number one, please to keep your microphone mute during the lecture. And then number two, you might turn on your camera if you wish, especially during the photo session. And then number three, for the Q&A session, you can use the raise hand feature and type your question in the chat column. I would like to acknowledge and warmly welcome Professor Dr. Heri Sutanto as the head of Department of Physics, Universitas Diponegoro, and Professor Dr. Engineering Eko Hidayanto as head of Master Program in Physics, and also Dr. Jatmiko Indra Suseno, the Secretary of the Department of Physics. Also, Mr. Sofyan Firdausi, Master of Science, today's moderator. And most importantly, Professor Dr. Engineering Takashi Yamamoto from the Department of Science and Technology, Tokushima University, Japan. Good afternoon, Prof. from Indonesia.
Yeah, good afternoon.
Okay, and of course, my greetings to all lecturers, students, and also to participants joining us via Zoom meetings. Today's lecture will focus on the topics of analysis of solid catalysts and environmental samples using a lab-based XAFS spectrometer. Ladies and gentlemen, it is my honor to introduce today's speaker. Professor Dr. Engineering Takashi Yamamoto has been a full professor in the Department of Science and Technology at Tokushima University, Japan since 2025. His main research interests include heterogeneous catalysis for acid-base reactions and sustainable chemical transformation, nano-level material design and characterization, also X-ray chemical analysis, particularly X-ray absorption spectroscopy using a laboratory-based spectrometer. In today's lecture, Professor Yamamoto will share his research on the acid-base properties of zirconia-based catalysis, surface and structural characterization, and simplified methodologies for XAFS data analysis, along with the role of lab XAFS in material science. Before we continue to the main agenda, let us begin our program with an Indonesian national anthem, Indonesia Raya. We kindly invite all of the participants to respectfully follow the anthem. Please wait for a while.
Mhm.
very much. The next agenda, we will have a photo session together. We kindly invite all of the participants to turn on your camera, and our documentation team will take some screenshots. Please, to all of the participants, to turn on your camera and give us your best smile. Okay, please, for the documentation team to take some screenshots. Okay, once more. All right, I think that's enough. Thank you, everyone. And to officially open our event, I would like to invite the head of Department of Physics, Professor Dr. Heri Sutanto, to give welcome remarks and also to open this event officially. Please, to Professor Dr. Heri Sutanto, the floor is yours.
Okay, thank you, Miss Suci, from the time for me. Baik, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Ya, good morning, all participant. Our Honorable Prof. Takashi Yamamoto from the Department of Science and Technology, Tokushima University, Japan, as today's speaker. Thank you very much for your kind willingness to share your knowledge and experience with us. We are truly delighted to have you here. On behalf of the organizing committee, I would like to warmly welcome Professor Takashi today general lecture with the theme about the analysis of solid catalysis and environmental sample using a lab-based XAFS spectrometer.
Yes.
I would like to introduce our committee chair, Professor Eko Hidayanto, who has worked tireless together with them team to make this event possible. We sincerely hope that this lecture will not only broaden our understanding of the subject, but also open door for future collaboration, its education, or joint research and publication. It's our wish today engagement can be the beginning of the stronger partnership and more intensive cooperation in the future. Once again, welcome and we wish you a fruitful and inspiring session ahead. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Professor Heri Sutanto, for the warm welcome and also to open the event officially. Okay, ladies and gentlemen, now let us proceed to the main session. I am pleased to hand over this session to our moderators today, Mr. Sofyan Firdausi. Hello, Mr. Sofyan, can you join us?
Thank you very much, Ms. Suci.
Okay, please, Mr. Sofyan, the floor is yours.
Yes, thank you. Good afternoon, ladies and gentlemen. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
My name is Sofyan Firdausi, and it's an honor for me as the moderator of this lecture. Okay. The duration of this lecture, if I know, is approximately 90 minutes, including question and answers. Professor Yamamoto, how long do you need for the presentation? Maybe 50, 60 minutes or
Yes. Yeah.
maybe
Maybe enough. Yes.
Yes, 15 minutes. Okay. This session will be divided into two parts. The first part is presentation from Professor Yamamoto, and the second part will be continued with discussion and question answers. Okay, without further delay, now we begin the lecture from Mr. Yamamoto. Please, time is yours. Professor Yamamoto?
Yes,
Okay.
yes. Yeah. Thank you very much, and I'm very happy to give me a chance, and I've never imagined such a nice ceremony. Yeah. Can I start?
Yes.
Yes.
Yes, of course, Prof.
Yes.
Yeah.
Okay, then I'll upload my file. Please wait. Is it okay?
Yes.
Yes.
Okay.
Yes, it's okay.
Okay.
Okay, thank you very much. And I am Yamamoto from Tokushima University, and I'm very happy, and this is my first experience to such internet lectures. Then I must apologize, and my English is very poor, and it may be troubles, but I'll talk about it, do my best. Yeah, and my topic is the title is analysis of solid catalysts and environmental samples using the lab-based spectrometers. And sorry. The outline of my topic is this one. Firstly, I'll talk about the X-ray spectroscopy and introduce a background and general lectures about X-ray fluorescence spectroscopy and XAFS. The second topic, second, two, three, four is my research topics, and the first two is metallion doped zirconia catalysts. The three is supported platinum catalyst precursors, and two or three is XAFS characterizations. The four is sediment at abandoned mine site, and this is not a catalyst. Yeah. The Tokushima is located here, and 3 hours from Kyoto, and 1 hour flight Tokyo, maybe around 400 kilometers, and exists in Ireland. And this nameplate is Professor Echo, and gifted me 60 years ago. Then I get these positions. Yeah. Yeah. Firstly, and I'll introduce myself. I was born in Uji City near the Kyoto. Kyoto is a city of matcha, tea cities, and Byodoin temples. And this is Byodoin temples and wood building 1,000 years ago. This is the 10 yen coins. This is the same as the symbols. Then, and I get the bachelor and master degrees in the Sapporo, Hokkaido universities. Then I get a doctor degree in the Kyoto, the heterogeneous catalyst. After that, and moved to the Tokyo and Yokohama. And the 1996, I went to Kyoto University. At that time, I met Echo. And he's a Dr. course student. I am assistant professors. 2 years, and I and Echo and work together. And in the 29, I moved to the Tokushin universities. My research interest is heterogeneous catalyst, X-ray chemical analysis, mainly X-ray absorption fine structures. Yeah, and this is a slide it had 2 years ago, and echo in echo ceremonies, and this is echoes and Professor Kawai and me, yeah, and this ones. Okay, and firstly, I talk about my city, the Tokushima. Tokushima is around here. It is a small island around to the sea. And Tokushima is this is in summers and outdoor dancings. And in this prefectures, and maybe 300 to thousand people, but at that time, million people together in these prefectures, and this is this one. And this is real pool, and the spin around the tight, maybe around 30 meters. Brazil, this is a nice scenes. And in we have a Tokushima ramen, and this is one. Then this is South Island, the cherry blossoms, and in winters, sometimes we have snow like this. And this is my cities. Okay, I'll move to the first topic. Firstly, I talk about the X-ray spectroscopy. This slide the interaction between X-ray and materials. This slide shows the phenomenon. Firstly, the materials and the X-ray the irradiated occurs. Someone ejected electron and in X-ray I put it. Then the kind of electron is a secondary electron or photoelectron or edge electron, something. And the kinds of X-ray is fluorescence X-ray or scattered X-ray or transmission X-rays. And large part of the phenomena heat exist. In my analysis, we use X-ray fluorescence or transmission X-ray. Then this slide shows the schematic diagram of the X-ray characteristic emissions. In the case firstly, and the incident X-ray comes, and the electron are ejected, like photoelectron. Four are generated. After that, and electron are how to say drop to the transition to the pole, and the energy the difference and the X-ray or radio wave are emitted. This is a characteristic X-rays. In a case, and 4 is K shells, it shows the K lines. This is in more details. And in the case of L shell, the 3 kinds of shell exist: L1, L2, and L3. And this is the principal numbers, and this is orbital quantum numbers. 3 shell exist: 2s and 2s electron, 2p half, and 2p3 half. Then this is a selection rule exists. It is electron transition is strictly restricted, and this is delta L. Delta L is plus minus 1. Then and L1 shell, the 2s electron cannot transition to the each s electron. Then and the electron transition is occurs between K shell and L2 and L3 shells. K1, K alpha 1 and K alpha 2 shell characteristic X-ray occurs. Then this energy is element specific. This is this plot shows atomic number Z and plotted and as a function of a frequency or the frequency characteristic X-ray lines. This is a Moseley law. It shows and Moseley found the square root of the frequency of the emitted X-ray is approximately proportional to the atomic numbers. It shows the energy is element specific. Then the characteristic X-ray can use to use elemental analysis. Yeah, then this is the two types of the X-ray fluorescence spectroscopy. There are two types, EDX and WDX. The EDX is energy dispersive. This is X-ray tube and the detector is energy sensitive detectors such as silicon pin, SST or STT like this. It is short measuring time and very compact size. The second type is the wavelength dispersive type, WDX. It is emitted X-ray using the analyzing crystals and the changing the energies and detected. By use of this one, it's a low background, high energy resolution, we can obtain the good spectrum. This is the typical spectrum. This mass spectrum. The top one is recorded with EDX style. Then this band is maybe 200 eV electron volt. But use of the WDX, the wave depth is narrower. By use of two crystals, very and high resolution spectra, we can record like this. Then this is the typical EDX spectrum. This is into inside the IC chip. Using this one, and we can see the many characteristic lines inside the gold or nickel or bronze or iron and steel. We can check these ones. Second type is a purchase device. This is inside the device, and using the device and this mass line we can see. Using these ones, and we can know we can carry out the elemental analysis very short time and very easily. But these spectra were recorded and Dr. Echo. And this is what to say 70 years ago, and Echo and published articles and like this and these journals, and Echo recorded many kinds of electric devices and analyze rare metal or noble metals using the compact type and the spectrometers. Like this, and we can carry out and elemental analysis very easily. This is the comparison to EDX and WDX spectra of stainless steels. I say the EDX and WDX is the difference in energy resolutions. You can see this is a stainless, contains cobalt and iron and manganese and many kinds of metals. But the peak is around 100 or 200 something, very, very wide. Then there are some peaks overlapped like this. But by use of WDX spectra, we can know the hidden spectra. If by use of the EDX as it is, we didn't know, we're not sure cobalt and iron coexist or not. But by use of WDX spectra, and we can carry out the precise and elemental analysis. Yeah, and WDX spectra, you can use in some case chemical state analysis. WDX can reduce the background and the trace amount element we can detect. But by use of the high resolutions, and sometimes we can use chemical state analysis. This is a K-alpha spectra of a sulfur compound. Then this is how to say, the brown is zero valent and 4 and 6. You can see the chemical shift exists, -2 and 0 and the coexist and -2 plus 4 and plus 1. By use of the what to say, the energies, we can use chemical state analysis, and not only the elemental analysis, but also use the chemical state analysis by use of the WDX spectrometers. Okay, this is commercially available X-ray fluorescence spectrometers. This is WDX, maybe an RAS. This is EDX. It is compact. In EDX can reduce compact and small facility we can with possibles. Then this is recently the handheld type EDX spectrometer is widely used and like this, and this is like this, and we can use on-site and very easy to the on-site analysis like this. Or this is a small type and total reflection, total diffraction X-ray fluorescence spectrometers developed by Kawai sensei, like this. Okay, next I'll talk about the X-ray absorption spectroscopy. This is absorption spectra of platinum recorded with high resolution spectrometers. You can see this is and the KH and L1, L2, L3H. You can see. Then this is these regions. If the X-ray absorption spectra were recorded using the high resolution spectrometers, and small but fine structures we can see like this. Then this and the fine structures contains useful informations about the chemical and chemical and electrostatic informations. Then this is a schematic of the spectrum. XAFS means the X-ray absorption fine structures. Then near this is the absorption edge, around 50 electron volt. It falls as X-ray absorption near its structures and absorption edge and near around 50 electron volt. In these regions, and electron transition to the unoccupied orbitals occurs. Then these regions contains information about the electronic structures and orbitals, something like this. Then and around several hundred electron volt, small but and structures exist. This is and the same spectra, but a different phenomenon occurs. This is a wide range. Then this region called as XAFS, extended X-ray absorption fine structures. This one. This is a different phenomenon. In a case and in an electron ejected, then this is propagated as a wave like this. Then if the another element exists and backscattered, then and the how to say it, propagation wave and the backscattered wave are interference, then and the absorption coefficient changes. Then this is inner shell transitions or scatters of photoelectrons. The same spectra, but different phenomena occurs in this spectrum. Then thus we can use some the informations about the target element. This is because the information about absorption edge, because this absorption edge is depends on the element and shells. Then by choice of the energies, we can use the element like this. Then we can know the information about the target element. Then in the chemical state and local structures. They obtain information that the oxidation state and the symmetry and coordination environment and coordination and coordinated and nearer kinds of element and the numbers or distance or something. Then and we can know the structures and informations, but the difference between the XRD and XAFS is XAFS we can know the information about the local structures up to the maybe 4 angstrom, 1 or 2 coordination spheres. And then not need how to say the long range structure ordering is no need. Then and this merit is high flexibility in the measurement of the conditions and samples. Then the X-ray diffraction pattern cannot know information about amorphous, but XAFS is okay because thus knows the information about the around 2 or 3 angstrom, first or 2 coordination spheres. Amorphous is okay. Then and the liquid and the gas is okay. And dilute sample is okay. Then maybe the lower maybe ppm levels or ppb levels sometimes okay in some cases. And the X-ray, this measurement is have the advantage. Its measurement is okay because if and X-ray or X-ray absorption spectra we can record it's okay. Then and the invited no need and vacuum no need. And water or coexistence of and liquid or gas is okay. Then we can record each measurement. It means we can know the information about the live fish, not the dried fish. Then this is we can know the information about the real state. Okay, I'll explain about firstly explain about the XAFS, extended absorption fine structures. And this is the spectra of krypton and brom atoms. Brom and krypton is the single atom molecules, and brom is two molecular atoms. Then the difference is the neighborhood is no atom around here, krypton, but brom molecules and near several angstrom and brom exist. In a case, and it emitted photoelectron wave prolonged like how to say go away as it is. But if in the neighborhood atom exists, then the wave scattered and back scattered again, and going and back and outgoing wave and backing wave and interference occurred. In a case, and the interference occurred. This is then by the use of the analysis of the back scattering. So this is this wave is changes by the kinds of the element or distance or numbers. If it short distance and back scattering wave is strong, and if coordination numbers were how to say it large, so large, or how to say depends on the element, and the scatter fields are shifted. Then by use analysis of the wave, we can know the kind of element. Then this is the methods of the typical analysis procedures. This is the X-ray absorption spectra of the copper foil. This is the fine structure we can see like this. Firstly, and background and estimated and background removals. And next, and also background and estimated. Then in background and remove and normalize to the edge jump like this. Then change to the wave vectors like this. This is the XAFS spectrum. Next, and this is in Fourier transform to obtain the radial structure functions. If so, and this is reflected like the radial distribution functions. This is not a radial and distribution function, but radial. It reflects the coordination spheres. It may be around 2 or 3 angstrom. Some scatter exists. This is a copper foil, and second or three coordination sphere we can see like this. After that, and this is next is we carry out the curve hitting analysis. This is my catalyst, and this is YBL3H XAFS spectra of our spectrum samples. And this is like this. Next, and these regions and inverse Fourier transforms like this. These regions inverse transform like this. If so, and different, how to say, and oscillations and envelope function or frequency change differs, and near regions and and how to say the low frequencies, but longer distance is high frequency. It changes like this. Then top and the top of the envelope function is around 5 angstrom inverse, or this is Q angstrom inverse. It means different kinds of elements exist. Then the next the simulation like this. Then we can know the first position sphere is oxygen. Then we can know the distance and the numbers like this. Then the next second coordination spheres, we can know this scatter is zirconium. Then this is distance is 3.660 angstrom and 7 like this. Then this is typical radial structure functions and calculating results. And this is like this, and this is rare earth oxides. This is this slide shows this spectrum shows our samples. Then the difference is and red one is our catalyst. Our catalyst is the second coordination spheres with determined the scatter is a zirconium, and the coordination number is like this. But in the case of the YB23 rare earth oxides, the scatter is not zirconium, the YB. It means and rare species incorporated inside the bulk, and the interstitial type solid solution were formed. Then we can know the distinguish this peak is zirconium or layers and ytterbium. We can distinguish like this, and coordination numbers and distance we can know using the XAFS. Next, and we'll explain about the ZENS. ZENS is a near range of the absorption regions like this near edge. Then this we can know several peaks like this and peak this. This peak is related to the transition to the unoccupied state. If then the occupied state no transition occurs, but in the case and the unoccupied orbital or the state transition occurs, and this is and these transitions and overlap the peak like this. Then the first point and the most important point is the use of the ZENS is H shift and absorption H changes with oxidation numbers. First, back to this one, and firstly the incident X-ray, the photoelectron and emitted, but the oxidation number changes, the threshold energy changes. Then, and you can see this is a mangan KH ZENS spectra of a mangan compound. This is zero mangan for zero variant, and green is oxide 2 plus, and this is a 2 and 3, and the spinel, and brown is 3 plus, manganese 4 plus, and K manganese 4, 0, 2, 2 plus, and 3, 4, 3. And you can see the absorption H shift to the higher energies, like this. Then if this is a different samples. If you compute the unknown samples, they compare the H shift. We can know the oxidation state and using by comparisons of the absorption H. Then this is a typical result of the processor. This is the second battery's materials. Recently, the second battery, the spectroscopy, then spectroscopy is widely utilized for the battery materials and charge and the discharge. The oxidation state, the changes and the charge or discharge like this, and the 2 plus and the lower energies, and 4 plus and higher energies. By the change of the charge or discharge and the absorption H and the changes, then we can know the in measurement the state or dynamics. We can know the we can know the performance of the secondary batteries like this. The point. The next is the spectrum shape depends on the local structures. This is the Zane's spectra of copper compounds with different oxidation numbers and the coordination environment. This is 0, 0. The red one is plus. The blue is 2 plus compounds. Then the coordination symmetry is D4H and OH and octahedral and tetrahedral. You can see the different compounds gave the different spectrum shape. This is because and this is how to say the coordination environment, the structure symmetry differs. Then the band structures of the orbitals are changes. Then the depends on the structures and the band unoccupied orbital level that changes. Then this is this is changes like this. This is then spectra is quite sensitive of the coordination environment. Then we can use and record these different compounds and unknown samples. By comparisons, we can distinguish. We can know the candidate of the unknown samples. Then this is the one of the results. Then spectra, it is possible to the qualitative and quantitative analysis of the unknown species. And this is in situ the Zen spectra of copper fly ash and during the de novo synthesis of dioxide. And this is 300 kilometers combined with the fly ash. Then we recorded our recorded spectrum is the circle one. Then by use of the combination, this and spectra can be produced by use of the chloride and hydroxides and these samples. We can know the These situations, these samples consists of the mixtures of this one and these fractions. Then using this one, so we change the temperatures and the samples, and we can we conclude that the dioxins are formed by using the kappa plus species like this. But the electron transition is restricted. The selection rule exists, and this is the electric dipole transition is the main component of the Zen structures. Then this electron dipole transition is strictly delta L. Orbital quantum number is plus minus 1. Then S electron transition to the p orbitals, but it is impossible to the transition to the d orbitals or s orbitals. Then the p electron can the transition to the d orbitals. But the p electron no. Then this is in these regions, and KH and L1H is transitions to S electrons. Then this is symmetry is sensitive. But L2 and 3H, this is 2p at half or 3 half electrons. Then this is in the transition to the d orbitals possible. The outer maybe outer shell is d orbitals. Maybe a large peak exists. This is not sensitive to the coordination environment. Yeah, the mixing or sloppy mixing, this is Zen spectra is very sensitive to the coordination environment. At that time, we explained the 1s electron and cannot transition to the d orbitals, but the t orbitals exist. And this is previous regions, and it may be mainly the 3 orbitals. In a case and in octahedral coordination environment, peak is very small, in general small. But in a case is tetrahedral coordination environment, and in these regions and d and p orbitals hybridize to make the hybridized the orbital. The new orbitals were formed. Then the peak, then the pre-H peak and more intense. Then this, how to say the KH then spectra of a 3D element is very sensitive to the coordination environment. And octahedral, in the case of octahedral, Fourier peak is very small, but in a tetrahedral and large peak exists. Then by use of the Fourier peak, we can know the coordination environment by check the Fourier peaks. This is a silica supported titanium oxide catalyst and titanium KH Zen spectrum. This is in the same loading amount, but prepared by the different way. This is prepared from the precursor is propoxide or acetyl acetate salt or DPM salt, if salt. Then the recorded spectra in this region, the peak phenomena are quite different, and small peak or large peak. It shows in the case of this one, this titanium species exists as an isolated titanium species. But this is the small peak is mainly the octahedral coordinated spectrum. They're using this complex and bridge peak intensity is half, but this spectra can be produced by the combination of the A and B spectrum, almost half. It means mixtures of the isolated tetrahedral species on the aggregated and octahedral species. Yeah, like this. Then by use of the comparison of the Zane's spectra, we can know the information about the chemical species or coordination environment like this. Okay, and this is the next is the ZAFS measurement. X-ray absorption spectra are usually recorded synchrotron radiation facilities and using the synchrotron radiation, the high flux and X-rays. This is a spring gate, and in Japan, maybe now around 10 beam line exist. Then maybe almost ZAFS experiment carry the singleton radiance facilities. But some X-ray absorption spectra can record using the laboratory type spectrometers. And this is the same as we have our laboratory, our universities. Then the SR facility and synchrotron radiation facilities exist and in the world. Recently, in East Asia and Singapore or Taiwan, the new synchrotron radiation facilities are opened, and maybe many, and the numbers increased. But if we want to record the X-ray absorption spectra, and we must go there, and we got the machine time. And it is the time it many time needs. Yeah, then the next and recently I usually record the X-ray absorption spectra using the laboratory type spectrometers, and in our laboratories, and this is introduced in the 1910, and then 40 years ago, and Dr. Echo and come to our laboratories, and this is the 1 year this, and we use this spectrometers like this. Then before coming to our universities, and 20 years ago, I've used next different type laboratory type spectrometers. Then then we use the two types of the laboratory type spectrometers. Then it is possible to the record and carry out the X-ray absorption spectral X-ray absorption experiment. It is possible, but this is X-ray flux and This is synchrotron radiation facilities and the X-ray tubes. But X-ray flux of the X-ray tubes and the X-ray facilities are quite differs like this. And this is X-ray tubes are like this, and maybe around here, maybe 10 times or much more different. Then, and the X-ray absorption experiment is possible using the laboratory type spectrometers, but is not we must choose settings and samples and experimental and the type of experiment. Then synchrotron radiation facilities are the high brilliance, high intensities. Then it is easy to dilute samples or time resolved samples or spatially resolved to experiment it. It is very easy, but this type of experiment it is very it is not easy to the laboratory type spectrometers, but high concentrated samples and we can record the in a transmission mode. It is okay for some screening studies or reproducibility test. It is okay. Then I think the major advantage is laboratory. The intensity of the X-rays are very weak. It means radiation damage is very low. Sometimes and high flux and synchrotron radiations, X-rays, and destroy the samples, hydroxides or and how to say, and reduce samples or cells or some things. But in laboratory type X-ray sources very weak. Then maybe and the risk is quite low, like this. Okay. Okay, and next, and they talk about our samples. This is background. And firstly, they talk about the metal ion doped zirconia catalyst. Okay, and the zirconia is we use, this is crystalline phase different. We use zirconia as an acid-based catalyst. And zirconia is a very unique samples. On the surface, base site and acid site coexist on the surface, like this. Then but this is the stable and some dynamically stable phase, and this is hydroxides and amorphous and below this temperature range, and metastable tetragonal, monoclinic tetragonal, like this. Then the zirconium oxide is widely used as industrially used, and for unique properties alpha olefin synthesis, and using the unique and acid base and combination with acid base pairs and alpha olefin synthesis or hydrogen transfer reactions. And next is the mixed metal oxides are also widely used in the oxygen storage release materials. And this is widely used for oxygen buffers, utilized for the automobile co-catalyst, oxygen and to control the oxygen concentrations. Then recently the SOFCs, solid electrolyte or solid electrolyte or solid oxide and fuel cells or something using sensors or something like this. And using the support. And this is the combinations of the tungsten oxide like this. It behaves as behave like sulfonic acid, like this, or by use of the support using nickels and the hydrogen generation, hydrogen production, and steam reforming catalyst. It utilize for hydrogen production like this. Then my research interest is the origins of one of my research topic is zirconia-based solid superacid catalyst. But today, this topic I omit this one, but I'll show you the I will already and prepared and propose structures like this, like this, like this. This is the common concept is mainly some of the doped metals are incorporated into the zirconium inside the bulk. Then in the case of the binary oxide, the tungsten oxide and zirconium oxide, and this phase diagram shows it shows the two solution could be formed. It means some are small amount of metals are incorporated into the metals. Then by using these ideas, and we introduce some dopant metals and prepare catalysts and design the catalyst and examine the catalytic properties. Then this is the procedures of catalytic preparations. Firstly, and we prepared and the zirconium salt and the hydrolyzed to the make the amorphous hydroxide. This is a very, very large surface area, maybe 300 square meters per gram. Then after that, and this is amorphous hydroxide and metal source and earth and calcine. This is a very, very simple sample preparation procedures and large surface area hydroxide in first prepared and metal source and incorporated and calcinations. Then we catalyst activity test is using the fixed state flow reactors like this. Then firstly, we use butanol decomposition reactions. This is a test reactions to investigate the acid-base properties. Then this is the second alcohol. Typically, if the hydration occurs, and usually, and second, and the inner organs should be formed, and using the Zysef orientations. But in a case and coexist in the acid and base site and alpha orphan formed the difference. But if and base exists and dehydrogenation occurs, then the use of these samples we can know the acid catalyst or base catalyst or acid base catalyst. We can distinguish and using the elemental compositions. This is the results. Then the zirconium oxides is have acid and base site. Then the alpha orphan, the terminal orphans obtain the high selectivity like this. Then by additions of group 2 or group 2-3 element did not change the activity or selectivity. But in a case and group 30 element and selectivity and quietly differs. In the case of the boron, this is like this. This is how to say the some acidity occurred. But in the case and gallium and indium and this is a dehydrogenated product that formed, and then this is quite different. Then there are two possibilities exist, and this is gallium doped zirconia is a noble base catalyst. Or another possibility is simple dehydrogenation to catalyst. Then this is 5 more percent. Next, we change the doping amount. And this is the result. And this means this is a doping amount in 0, 1, 3, 5, 10, and more percent. And this is a gallium oxide. The yellow circle is conversions. Then this is product selectivity, and this is as the purple is keten, the hydrogenation product, and green the common origin like this. Then you can see the small amount dopant and 1 more percent additions, and the conversions and enhanced two times. And ketone, the methylated ketone, the dehydrogenated product, and selectivity obtained high yield like this. Then the selectivity did not change up to the 5 more percent like this, but more than the 10 more percent, the selectivity changes and internal orphans amount of increase like this. Then this is similar to the that over and oxide as it is. Then the next, and we first recheck the XRD patterns and to check the gallium ion the incorporated or aggregated or some things. Then this is amorphous and tetragonal zirconia phase are observed. Next, we check these regions. We plotted the D values and plotted as a function of the doping amount. Then it shows the original phase and by increasing the doping amount, and the D value just shifted with increasing temperatures. It means maybe and the first time the incorporated and the D value changes. But this value, this D value is constant and more than 10%. It means further additions and that does not in gallium ion does not more incorporated in the samples. Next, and we recorded the gallium cage XAFS spectrum. Then this is the radiostructure functions. Then we can check the different types and the low dopant amount, and the second peak appeared around this year, and higher loading amount and higher doping amount, the change differs. Then by curve fitting analysis, we can know the low doping amount. This is the second scatterizer and zirconium. It means it suggests gallium ion incorporated into the bulk. But and the high doped amount and this shape is close to that of the gallium oxide. Maybe it is aggregated. Next, we try to the quantitative analysis by the Zanes. This is a cage Zane spectra, and the amount. You can see the spectrum shades, the changes and like this changes and continuously like this. Then isotonic point exists. Then we presume this sample is a mixture of the how to say the incorporated type and atomically dispersed one and aggregated one. Then I estimate the linear combination analysis to investigate the fraction of the mixtures like this. It's 5% like this, and all spectra can be reproduced by use of the aggregated one like this, and oxide, and isolated one like this, and we can to reproduce like this. Then we estimate the fractions of the solid solutions like this, and the low doping amount is almost 1%, and decreased like this. Then the Bayer is multiplied by the fractions of chains and the content amount. We can calculate the fractions of the compositions of the solid solutions. I'm sorry, this is a Japanese character. This means the compositions of the solid solutions. Then the fraction and the fractions of solid solutions and the component. This is almost the same. It means 5 more % is at maximum. It means gallium ion incorporated into the zirconium oxides, but 5 more % is maximum. Then this is the D values. Then this is this and the D values are firstly the decreased and constant. Then the position is almost identical. It is agree with Zen's analysis and X-ray analysis. Then this is a summary of this catalyst. Then the small amount of the gallium ion, incorporated into the zirconium bulk and to forming the solid solutions. This atomically dispersed and gallium ion, this is quite active for dehydrogenation to make the K10. But this concentration is up to 5 more %. In the case, the aggregate species is and this is active for the dehydrogenation and behave as a solid acid catalyst like this. Then the next, and we and applied this and samples the ethanol conversion to chemical fuels. Recently, the carbon neutral is in the key issue to replace the fossil fuels. Then we use that, and recently the biomass compound of the chemicals is very attractive in the intact. Have a great interest. Then this catalyst is very active for dehydrogenations. It means firstly the ethanol to form the acetaldehyde. If so, next is carbon forming reaction should be proceed. Then today I talk and I didn't talk. I don't talk about in detail, but in the presence of waters and in the water vapors and 40%, this catalyst and promote isobutene formations and we investigate and reaction pathways or active site like this, and the and dehydrogenation, the solid solution or like this ones. Yes. Then the next, and we first to investigated the gallium ion, but the next we changed doped metals and 3D element. And calcium and 3D element or fourth period element calcium to the couples. Then you can see the calcium, scandium, titanium, there's a little influence and the catalytic activities. But in the case of vanadium and copper and zinc is in different tendencies. And the copper found to be quite active for dehydrogenation activities, and maybe copper and copper zirconia catalyst is quite active for ethanol dehydrogenation reactions. Then this copper zirconia catalyst is known to active for direct ethyl acetate synthesis from ethanol. Then the IR applied this catalyst to direct ethyl acetate synthesis. And this is in the absence of the water vapors, and the temperature is 200 to 220 Celsius Kelvin. And it has been known that this catalyst is active. Then, but we found the catalyst selectivity is different and depends on the crystalline phase of the zirconium. Then this is and we found amorphous type catalyst is best ethyl acetate yield and selectivity. But the monoclinic catalyst is worse selectivities, and it has been the crystalline phase dependencies have been reported by other research groups, but the tendencies are quite different. But we prepared and many more than the 30 kinds of the copper zirconia catalyst, and using the same and raw materials. That we can conclude the amorphous is catalyst is best and like this one, these people. I'll talk about the catalyst preparation procedures and how to control the crystalline phase. Then the preparation procedures is quite similar. Firstly, the zirconium and salt is the hydrolysis to obtain the zirconium hydroxide, and calcined without metal additions. Then below it 300 Celsius and amorphous, but more than the 400 Celsius, and the monoclinic phase appears. But by using this amorphous phase, it's hydrothermal treatment. The different pH gives a different pH, and the acidic conditions and gave the monoclinic phase, and the alkaline, the basic conditions gave the tetragonal phase like this. Another way is the loading pathways. The zirconium amorphous zirconium hydroxide in calcine 600 Kelvin. And without metal additions, it forms a monoclinic type, but 10% copper additions after 400 Celsius, and this is remained amorphous. But and 500 and 600 Celsius, and it and tetragonal. Or another way is calcium or ethylene doped zirconium and the doped like this. This is tetragonal type like this. Then this different type is how to say the firstly the calcine and monoclinic produce and doped like this. Then hydroxyl treatment like this. Then like this, and we can control, we can obtain the kappa zirconia capitalist and amorphous tetragonal type, monoclinic type, and then we do carry out catalytic reactions like this. Okay.
Professor Yamamoto?
Hi.
Yes, 4 minutes left. Please.
Okay.
Okay.
Okay, and then the next I'll talk about the skip the second topics like the 4 topics. Okay. Okay, and the next topic is about the sediment that the abundant mine they did. Old mine site, and I use the analysis of the laboratory XAFS and laboratory the handy type atomic emission spectrometers, and this spectrometer is Professor Echo and use at Kawai laboratories. Yeah. And this is portable type and how to say the liquid atomic and emission spectrometers. Yes. Yeah. And anyway, the abundant mine site this is pictures of the abundant and old mine site in Tokushima. Maybe 30 minutes drive from the universities, and the West Rock but leave as it is, and and small drainages is and erosion in the go away as it is, but without any treatment. And large mine site is and how to say controlled, but small and abandoned mine site is leave as it is. Then and my investigate about the and how to say the leachate of I investigated and leachate of the heavy metals on the state of the element. Then this is I'll go to the abandoned copper mine site near the Tokushima prefectures. This is pictures, and I went this mine 10 years ago. The inside like this, and how to say the river as it is, and wastewater and go away like this. Then this is the copper mine. Then this is at high, how to say the high electron conductivity high. It means maybe and many minerals contained, and near the rivers it's 10 times, and high electron conductivity is 10 times larger. It means maybe many metals contained. Then I investigate the state of the copper in the sediment and in the soil around here, and investigate the kappa content in the wastewaters over how to say in the leachate solutions using the handy type spectrometers. Yeah, this is like this and like this and then this is a experimental setup, and either sampling the sediment or soil samples and the dried and ground, then the dried and this one and the hydrochloric acid and the mixed and filtrations. Then the I analyzed and this is a kappa state investigated by laboratory type spectrometers. Then the content determined with the X-ray absorption and elemental analysis also carried out. Then the leachate solutions are recorded using the laboratory novel type of portable analyzers. Yeah, this is the novel type, a new type and atomic emission spectrometers and developed by the professor Takamura, the Hokuriku Sentai Universities. And this is a very unique and very small chip exists and maybe small, maybe small and how to say small parts exist and pulse type high voltage applied and this is evaporated and this is plasma formed and Professor Takamura said and in this region maybe at maximum 3 or 5,000 Kelvin. Then and this was an atomic emission occurs and using the spectrometers and to carry out quantitative and qualitative analysis. Yeah. Then this is and paper recorded by the echo. Then in using the spectrum, it can atomic emission spectra and depends on the element and sodium or current. This is an echo and recorded maybe 17 years ago. Yeah, like this. Okay, and this is move to the result. And this is emission spectra over the leachate samples. Then in these regions, we can observe an emission line from couples from soil and sediment, right, like this. Then it contains a lot of other elements and to determine the concentrations. Internal addition method we applied to determine the concentrations like this. Then the lower limit of the detection limit is estimated to be the 16 ppm and this sample is 147 ppm. Then the quantitative analysis results are like this, and to check the accuracy and the precision, and we compare the flame atomic absorption spectra. It means maybe almost the same levels. Then maybe this is battery available. No there are no need to the batteries. Then we can, and this is how to say, the screening study. It is useful. Then next, and the X-ray spectrometries and like this, and using these spectrometers, we examined the three type experiment carried out. Firstly, X-ray fluorescence spectroscopy. Then using these ones and excitation source and molecular halide that it monochromized this using these settings, and the Care halide is it used and inside this, and the silicon, this is X-ray emitted, and this one, and this is samples and silicon beam detectors. Then X-rays in the elemental analysis are carried out. Then the qualitative analysis is using the X-ray absorption spectrometries. Then the next is the state of the couple is using this spectrometer XAFS, and then the analysis carried out. This is the result of the XRF. If so, then these samples contain the manganese and the iron and copper and zinc. Then the sediment and soils contain the coppers. Then we determine the concentrations. These samples contain the 3 or 2%. 2%. We can determine the concentrations, and the soil is maybe 0.28%. Next, and the couples and XAFS analysis carried out. This is a Zen spectra of samples. I'm sorry, this is a Zen spectra. Then this is a copper and different sample and sediment samples. This is a first derivative. You can see the sediment, the shape is looks similar, but and by use of the derivatives, and you can distinguish the samples. You can see the sediment samples on the basic and copper sulfate or carbonate sulfate is very close to here. Then we assign the copper species is and inside the sediment is maybe basic sulfate. Then the XAFS, we can succeed it in the XAFS spectra. The XAFS spectra can suggest this reaction that if the hydroxide, the second peak exists, but there are no peak, then this sample is not copper hydroxide. Maybe it is possible. Maybe copper species in the sediment is basic sulfate. Maybe this is conclusions. Maybe this copper is I suppose the copper sulfide is oxidized, and firstly the sulfate and dissolved into the waters. But the more than the maybe in acidic conditions and exist in how to say the solutions, but in the case if the pH values are up, it is precipitated to form the hydroxide. But there are many sulfate ion coexist. Then maybe basic copper solution, basic copper are formed. Yeah. And this is the summary of the mark. And I'm sorry, I skipped the preparation for species composition and the copper analysis. But using the laboratory spectrometers and catalyst preparations and examine the catalyst design and local and bulk, bulk structure examined and like this and the portable elemental analysis are also carried out. Then and this is the characterizations or my research and interest is very simple and easy method we'd like to develop and this and using the spectrometries. Thank you for your kind attention. This is after that and Professor Echo came two times and firstly the to 3 years and then Echo comes into laboratories. And this is my wife and my son. This is my son. And 2 years ago, and Echo and come to the Tokushimas and like this and this. And I'm sorry. This is that's all. Thank you for your kind attention.
Thank you very much,
Professor
Professor Yamamoto, for your excellent presentation. Before the discussion, I would like Professor Eko Hidayat to give short, brief insight or comments, please.
Okay, thank you, Mr. Sofyan. Honto totemo subarashii ne, sensei.
いやいや、申し訳ない。
Thank
あ
you
り
very
が
much.
とう。
Thank you for your presentation, next presentation. So I will talk here with mixed language, Indonesia and English. So para mahasiswa sekalian, all of my student, Yamamoto Sensei is for me is very great professor, very great teacher. Not only give me lecture about spectroscopy, X-ray, etc., but also he give me excellent philosophy like that. Yeah, really, really, Sensei. It's a deep impression for me. Where I remember when we do experiment using micro emission like your presentation last minutes ago. I very remember when we testing a liquid sample when then we didn't find sodium
Yeah.
in the sample. You
Ah,
remember?
yeah.
Yeah.
Okay, yeah.
I remember that sodium, natrium, sodium, like this.
Yeah.
The wavelength is about go HQ nanometer,
Yeah.
589 nanometer. Like.
Yes, it
But
is.
in this
Okay.
sample, we cannot find this.
Yeah.
So you
Yeah.
explain to me, and Echo, if you find in your life. So if we didn't find any kind of element, for example. For example, we examine a sample and we get X element. So you must say this is X element, not Y or Z or other. So you never lie to say anything. Jadi demikian. Jadi para mahasiswa sekalian, jadi beliau tidak hanya sekedar memberikan ilmu bagi saya spektroskopi umumnya, tapi dalam eksperimen beliau ini juga memberikan nasihat yang intinya ya ketika kita menggunakan spektroskopi ini kita bisa belajar tentang kejujuran begitu ya. Jadi this is I mean that 100% science and religion are very closely related. This is Yamamoto Sensei. I always remember your advice like this. So I hope that spectroscopy that you teach to me and another, I think, will be give me a lecture about the honest in all of things. That is was our religion teach like this. Jadi kira-kira seperti itu. Hikmah di balik belajar apapun ya, termasuk spektroskopi adalah seperti itu. Ya, semoga kita juga bisa belajar dari apapun ya, termasuk fisika, spektroskopi maupun material ataupun yang apapun yang kita pelajari, hendaknya tidak hanya sekedar dapat ilmunya, tapi juga mendapat ilmu filosofi seperti itu. Okay, Jamal Sensei, just like this, I say like this. Maybe my student or lecturer will ask to you. Okay, please, Mr. Sofyan to.
Yes, thank you very much. Professor Herisnanda?
Okay,
Would you
thank
like
you,
to-
Mr. Sopian, for moderator in this session. Okay, Prof. Yamamoto, thank you for your lecture for today. Regarding the sub method, I have two questions about this method. The first question, what specific advantage does sub offer XRF when analyzing to the local atomic and electronic structure, especially of solid catalyst?
Yeah.
The second question, how can sub provide unique insight into the oxidation state and coordination geometry of active site in solid catalyst, because that the information is difficult or impossible to obtain using the XRF or XRD technique. Yeah, thank you very much for your lecture and answer. Yeah.
How to say about that? This is a very, very useful to the investigator, and this is powerful techniques, but not always almighty there, because XAFS is the distinct element, but the scattered atoms didn't distinguish between the near atomic numbers and oxygen and the nitrogen that can be distinguished, but for oxidation state analysis, maybe it gives and relatively, and I think reliable. Maybe and I think XPS is widely used to investigate the oxidation state. But the XPS is sometimes, and how to say, the oxidation state is changes and during measurement, and for especially for transition metals or noble metals. Maybe I think I think transition is how to say oxidation state analysis is maybe for novel maybe oxidation state analysis is maybe thus is maybe I think the very very easily, I think.
Good. Okay, with the compare and XRF or XRD techniques for the same case?
Yeah, but yes, and maybe maybe almost the same, and SR is it takes a long time. Maybe and maybe this is I think our today I explained the two topics and the same results. We can maybe the same results we can obtain the laboratory spectrometers and synchrotron radiation facilities. But I'm afraid that sediment samples. But if how to say the microbeam analysis maybe destroyed, it happens to the change to the oxides. Maybe だから、bending magnet beam line is bending magnet beam line is maybe the same results we can obtain. But say if using the if use the micro beam or undulated beam lines, maybe SR beam line gives a different possibility to give the different results. Maybe in some case and to change the different results, but usually
Okay.
same results.
Okay. Thank you, Prof. Yamamoto. Can you insight about that the sub method? Yeah. Once again, thank you very much. Okay.
Thank you.
Okay, thank you very much. Next question from Sabri Ali Ansari. Go ahead, please.
Mas Sabri, please.
Okay. Thank you for Mr. Yan. I would like to thank you for Professor Yamamoto for the wonderful lecture. I would like to ask about the type of the lab spectroscopy have the potential to purely replace or only complementing the use of cyclotron facility for the future XAFS studies?
Sorry, I'm sorry. Again,
Test.
how to say how in it have the how to say it.
Does the type of lab spectroscopy have the potential to purely replace or only complement the use of cyclotron facilities for future XAFS studies?
Oke, I check.
Suaranya mantul, Mas.
This, なるほどね。Yeah, maybe my spectrometer is how to say this is 20 times ago. Recently, Professor Seidler developed the new spectrometers. Their spectrometer is very nice. Then it maybe impossible to replace all because dilute or time resolved and how to say that this is and dilute time resolved special result it is maybe maybe difficult, but in many samples maybe almost how to say 70 or 80% of the samples are you can we can record use the spectrometers. My detector is a scintillation detector. This is not good detectors. If and change the now recently the detector growth and development detectors are very good. Maybe not replace, but maybe large part of the ZAFS experiment can cover using the laboratory spectrometers, I think. maybe compensation, but covers and
Thank you.
It is okay, Mas Sabri Ali Ansari?
Yes. Yes.
Okay. Okay, one question please from audience. No? Cukup ya? Yeah, yeah. From Ardila, please go ahead.
Okay, thanks so much, sir.
Yeah, Ardila, please go ahead.
Okay, thank you for the great presentation. I would like to ask about XAFS based on your explanation. What are the explanation of XAFS in the testing catalyst material or other functional material commonly using in medical physics or radiation physics, such as phantoms, radiation shieldings, and other materials? Thank you, sir.
okay. So sorry again. Now it's mute. Now I mute. Now I mute.
Unmute.
Sorry, Mr.
Uh,
What are the application of XAFS in the testing catalyst material or other functional materials commonly using in medical physics or radiation physics, such as phantoms or radiation shielding and other materials? Thank you, sir.
Yeah, maybe maybe my research interest is metal oxides and acid-base catalysts and how to say now so skip but I'll topic is oxidation state analysis of the platinum compound. Recently, platinum 3H XAFS is widely utilized to investigate oxidation state. But recently we know the using that and peak the peak intensity is peak estimated using the peak functions and peak function, but the choice of the peak function drastically change the drastically change the results. Then I'll design the platinum catalyst and in addition and simple analytical method I'd like to investigate. It's okay?
Okay, thank you, sir. I wanna ask about one question again, about EDX. Based on your explanation about EDX, in your
EDX.
slide, how is the energy dispersive X-ray spectroscopy and CT image on phantom material in medical physics? Thank you, sir.
Sorry?
Based on your explanation in your slide, the beginning of your presentation, about EDX, energy dispersive
Yes.
X-ray spectroscopy. How
Yes.
about the relationship between EDX and CT image on the phantom material in medical physics.
Sorry?
About energy dispersive
Yes.
X-ray spectroscopy, how the relationship between EDX and CT image on phantom material in medical physics.
I'm sorry, I understand the next meanings.
Sorry, sir. How about the material phantom in medical physics? If from result EDX, energy dispersive spectroscopy.
Sensei, I can help his question. She asked, what is the relationship between EDX to measure, for example, material in medical physics?
Yeah,
For example,
yes, medical physics or radiation
Material,
physics.
sorry,
how to measure, for example, using EDX or other to for material in medical physics, for example, phantom.
medical?
Medical physics, material in medical that usually used in medical physics.
Sorry, and what is meti? What is
I mean that in medical physics, usually we use, for example, phantom or phantom. Then how to measure phantom with EDX, WDX, maybe like this.
I'm sorry, I don't. Phantom is
A kind of material using in medical physics, material or radiation physics.
material.
It is a kind of material, something. For example, like ceramics, metal, amorph, etc. Just a kind of material, but it's used in medical physics like this.
You mean the choice that you mean choice わからんな。そういえば何も質問されたかちょっとわからなかったな。それ。
I mean, it's commonly how to use EDX for to measure material, for example, phantom. That is a kind of material in medical physics or radiation physics.
How about your relationship about the measure of EDX about phantom material?
Phantom material.
Maybe for element analysis, EDX is maybe enough, but sometimes how to say maybe the unusual and EDX okay, but sometimes and overlap, then to check the second peak, and it is important to check the results because the K alpha line always contains K beta, the set of alpha and beta, and L alpha or L betas. Maybe in most cases, EDX is enough. But to how to say it is important the set existed, for example, theなんだろう。to check the overlap in the table and tables and another peaks, then it is enough maybe.
Okay. I think it's been 2 hours. Okay. Thank you very much again, Professor Yamamoto, for your valuable lecture. Time back to Ms. Suci Fanyandari, please.
Okay, thank you very much, Mr. Sofian Firdausi, and also Professor Takashi Yamamoto for the very insightful lecture. Now we are coming to the certificate presentation. As a token of appreciation to Professor Takashi Yamamoto, so I kindly invite Professor Heri Sutanto to present the certificate virtually to Professor Takashi Yamamoto.
Okay, thank you, Dr. Suci, from time to me. Professor Yamamoto, thank you for your sharing your valuable knowledge about analyzing solid catalyst and environmental sample with an spectrometer. Prof. Eko, can you share the certificate?
Just a moment, please. Otomatik udah saya send, otomatik. Bentar. Deh.
Okay.
Just a moment. Oke.
Okay.
Kita share
Can
ya,
you share
share bentar. Oke.
certified for Prof. Yamamoto?
Mas Faisal bisa diganti di samping. Demonstration can you see on your screen, please?
Yes.
Oke, Prof. Heri silakan, please.
Sudah, belum? Oke.
Oh.
Okay, Prof. Yamamoto, please accept the certificate as a token of our appreciation for your willingness to be our guest lecture speakers today. We hope to see you at the Department of Physics, Diponegoro University again in the future, and we are looking forward to possibility of Professor Eko Hidayanto collaborating with your research and publication. Once again, thank you for speaking on the general lecture. Sumimasen. Thank you. Yeah.
Okay, thank you very much, Professor Heri Sutanto. And ladies and gentlemen, this concludes our general lecture organized by Department of Physics, Universitas Diponegoro. And I am on behalf of the organizing committee would like to send our gratitude to Professor Takashi Yamamoto for the very insightful lecture today. And also to Professor Heri Sutanto, Professor Eko Hidayanto, for their support, and also to Mr. Sofian Firdausi for moderating today's lecture, and all of our participants obviously for joining us virtually. We hope today's lecture will be fruitful and engaging to all of us. Once again, it has been my pleasure to be host of our event today, and thank you very much, and see you in our next academic agenda. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Good
Thank you,
afternoon,
Prof.
everyone.
Yamamoto.
Thank you, Prof. Yamamoto.
Thank you,
Thank you,
Prof.
Yamamoto
Yamamoto.
Sensei.
Thank you.
Hontoni arigato gozaimashita. Next time we will. I hope we can visit you again directly to Tokushima. I hope like this.
Yeah, and then always welcome. Always welcome.
Okay.
Yeah. You
Okay,
and
see you next time.
Is always welcome.
Mata Raisa nih.
Okay.
Okay, thank you again.
Okay.
Okay. Okay.